Hi, we are continuing the discussion in chapter 4 for the pipeline design, and we are moving to the topic of instruction level parallelism. And before we get into that, let's give a small or a quick introduction. Uh, uh, Basically, we started this chapter with a scalar non-pipeline processors. Um, and this has helped designing processors for some time. Then people moved into pipeline processors, where we have our MIPS processor is a good example of the uh, five stage processor. Then people realized that they need to do better. Why better? Well, if you look at the CPU time equation, you will see that what we have it is instruction count times CPI times cycle time. Okay. So what people did, they figured out if they could improve or reduce the cycle time by using super pipeline, further dividing these stages. And there came the idea of super pipeline. Many stages you have in these microprocessors, probably above 30 stage, 40 stage, and that had helped the cycle time to be reduced and therefore reduce the CPU time. Unfortunately, these deep pipelines or super pipelines have many problems, and mainly if you have issues with loads and jumps, and you have to wait. It turned out you waste lots of cycles to resolve the jump and load instructions. In addition to that, you have whenever you add these pipelines, you add registers and they tend to consume power. In addition to the latch and flip-flops become part of your cycle time, because this the cycle time. It is really, if you look at it, it is the computation plus the time for the flip-flop. So if you keep dividing these computation times, then comes a time where your flip-flop becomes significant part of your cycle time, which indicates an inefficient way of utilizing your cycle time. Then people moved to another architecture. They said, okay, let's figure out a better way to do it. How about if we issue multiple instruction per cycle? So instead of having one instruction fetch, we'll fetch two instructions, and we will decode them and execute them. Okay, so let's do this for now, and execute them. All right, and access the memory and write back. So two instructions at a time. Then we moved to another two instructions, etc., etc. And these guys, this is what we call the multiple issue processors. And these people, what their plan of attack is to reduce the CPI. So by reducing the CPI, they are not reducing the cycle time. They are reducing the CPI, making the CPI less than one, because a half or a quarter, and therefore you reduce the CPU time. So now you can see the flavors of attack, or the flavors of designs to attack the CPU time. The deep pipeline attack the cycle time. The multiple issue attack the CPI. Okay. Now, with that introduction, of course, the goal is reducing what? CPU time. Okay, so with that introduction in mind, let's go to the lecture here, and basically we are enhancing parallelism at what level? Instruction level. Well, we do we have parallelism at different levels? Of course you do. You have at the instruction level, you have at the thread level, you have at multi levels, you have at the bit level. you have at the loop level. So right now we're talking the instruction level parallelism. And as we said, deeper pipeline attack this. Unfortunately, they have their problems, and they serve the purpose for some time. Then people departed from architecture to the multi-issue architecture. And basically, the multi-issue architecture, basically, you are trying to execute more than one instruction. So when we say four-way, it means we are executing four instructions per cycle. And if you have four-way multiple issue processor runs at 4 gigahertz, then you hope that you will have 16 billion instructions per second. That is your peak, by the way. So we say that the peak CPI is a quarter. The peak instruction per cycle is 4. Notice that instruction per cycle is, instruction per cycle is equal 1 over cycle per instruction. Okay, and the CPU time equation, we said it's instruction count times CPI times cycle time. Again, I'm getting this, times cycle time. Okay, so notice when I reduce the CPI, what happens? Reduction of CPI reduces the CPU time. Okay, so that's the plan of attack for the instruction level parallelism. Okay, again, I'm going to go to the whiteboard here, and let's just take a look at what we want to prepare ourselves for. So in terms of multiple issue, the multiple issue processors, uh, they kind of divide this into two groups. We have those. Let's see if I can do this. Whoops, uh, that's not what I want. Let's see if I can do this. Okay. Okay. So the multiple issue processors, basically, they have this criteria. I don't like even what I just did. Let's just do that. Okay. Uh, we can define the multiple issue as a static multiple issue and dynamic multiple issue. Again, multiple issue, it means I am executing more than one instruction per cycle. Okay, so we have this static, and static, basically, in the static multiple issue, it is the compiler which issues those instructions. And remember, the compiler compiles the instruction before runtime. While in the dynamic, it is the CPU which issues those or chooses those multiple instructions. Okay, so one happens in the compiler time before run of the program, and the other one happens during running the program. During running program. Okay, so in this case, we would like to say who selects the multiple instruction to be executed instructions. Okay, to be executed. If we have the compiler who chooses those instructions, and in fact, it will they will call it static issue, static multiple issue. And if the CPU chooses those instructions, it is dynamic. Okay, good. So we'll move on to the next point here. And the next point is, by the way, when the compiler chooses those, it will put those instructions in what we call packet. Okay, so put them in a packet. So these are the instructions. So this is instruction 1, instruction 2, instruction 3. For example, packet of 4. Okay, we call those packets. Now, sometimes here we get the help of a compiler. We do sometimes to make the CPU do its job more efficiently, but it is mainly the CPU who chooses those instructions. Now, In terms you know that we will get hazards. So hazards, who resolve them? Well, the compiler resolves them here. The compiler has to detect hazards and avoid them. Detect and avoid. Okay, so it has to avoid as many hazards as it could in this. There will be hazards during runtime, but mainly it's the compiler when it puts those packets. It has to, for example, you wouldn't have two dependent instructions in the same packet. That's illegal for the compiler to do. Now, in the case of the CP dynamic, the CPU here, the CPU here detects, detects and resolve hazards. Okay, detects and resolves the hazard because it is the one which chooses those instructions, so it has to be able to detect and resolve. So you can see the static multiple issue, it's all about the compiler doing all the job, and the dynamic, it's all about the CPU doing the entire job. And with this introduction, let's go back to our so we have the static multiple issue and dynamic multiple issues. So the compiler really groups those into packets, and those packets will be fetched by the CPU. But in the case of the dynamic issue, the CPU really, it's the one which chooses the instructions to be issued. Excuse me. Now, in terms of we will use what we call speculation. And speculation, what it means a guess. We need to do some kind of a guess at some point in the execution on a branch or what have you. Then we execute until we complete and we get our decision. Then we check for our guess. Okay, so we check our guess. Was our guess correct or not correct? Okay, if it is correct, then we complete the execution. If it is not correct, we guessed wrongly, we roll back. Roll back, it means go to where I did the mistake. So for example, if I have a branch if equal, okay, and I had da 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 and have L1, so and L1 is here. So now I guessed, I made a guess, I made my guess that I will jump here because it takes long time for me to determine if this is a branch that will be taken or not taken. So I made a guess. This is my guess. So over here, I fetched and I executed the instructions. Okay, this is my guess. Whoops! Then I realized, whoa! After I executed this instruction, that was the wrong guess. So what do I have? I kick out these instructions. Okay, flush them, and I roll back and I go and continue the execution in the right place. Okay, so basically the guessing, we're trying to start the operation as soon as possible. Okay, we're greedy, we don't want to wait. But then we have to check whenever we complete or we know for sure the status of our guess. If it is correct, we complete, or otherwise we roll back. Prime examples of those, of course, the branches and the load. And the load instruction, we have to guess the address for the load, the data we are loading, etc., etc. Because the load tend to be also a painful, painfully long, painfully long, especially when we start talking about missing in the caches, etc. Now, of course, if we have, you can see that the compiler some need to do some reordering of the instructions to do some fix up. So it has this flexibility. So so it will optimize, if you will, the execution for the CPU. Now, you can talk about speculation and exceptions, and I'll leave this as a reading material for you. But let's now focus on the very first type of multiple issue processors, that are the static processors. As we said, it's all about the work of the compiler. The compiler groups the instructions, and groups them into packets. So it put, like, for example, two instructions in packets. And those, we would like to call them very long instruction word, VLIW. And the processors that executes those, we call them VLIW processors. So the compiler will put those instructions in packets, and when we issue those packets, we are really issuing a VLIW instruction. Okay. Now, here it's the compiler responsibility to remove all the hazards, as we have indicated earlier, through reordering. Okay, it has to make sure that no dependency within the packet. Possibly there might be dependency between packets, so it has to do some pad of no ops. No ops, it means no operation. Okay, so if there is, if it has a packet, and there is a packet and there is a dependency here, and we need to wait for a cycle, so it will insert a no up packet, where basically we say we are not executing anything. We are just waiting. This is a stall cycle, but we are issuing a no instruction, which is kind of weird, but that's basically what it is. Okay, now, so in terms of a static dual issue, okay, so how can we issue two instructions at the same time? Well, typically the two instructions that we try to execute, they are not of the same time. They are different types. One of them will be either ALU or a branch, and the other one will be a load store. Okay, so in this, for example, you can see now when we move in the pipeline, we will fetch these two instructions, and then in the next cycle we will decode them, and at the same time we fetch another two instructions. And in the third cycle, the very first two will execute them, the second packet we will decode them, and then we have a third packet, etc., etc. Notice the addresses here, the addresses. Since I'm fetching two instructions, I can fetch this packet, and this packet has to be 64-bit aligned. Why 64-bit aligned? Because I have every word of those is 64-bit. I'm sorry, 32-bit. And this word, which is instruction, 32-bit. And therefore, my packet is how long? 64-bit. And we know that MIPS architecture likes to have things lined and clean, aligned and clean. So your packet has to be 64-bit address aligned. Okay, so now we know that these instructions cannot be arbitrary instructions. We will choose one type, and the other one. And typically in those static issue processors, what we do is that we will call this packet. We will call this uh, slot 0 and slot 1, and basically, if you have more, you can have slot 2, slot 3, and basically it means that this is the instruction that will be executed in slot 0, and here is the instruction executed in slot 1. Typically they are different instructions, and it depends on the architecture. Now, in our architecture, we said in slot 0 we can execute ALU or branch, and here we can execute store or load. So what kind of stuff we need to update our hardware to accommodate such a change? Now, in our hardware, everything looks the same, except, let me get the highlighter. Except you can see that here we are issuing extra instructions. Instead of one instruction, we are issuing two instructions, and this is the packet right here. And also my register has to supply for me four registers that are read, that I can read. These are for the ALU, the first two for the ALU, and the second two for the load and store. Okay, one register for the address calculation, the other one for the store operation. And then so this is in what stage? The ID stage. And then in the EX stage, notice I need an extra ALU. And this extra ALU is used to compute the address along with the ALU, which will compute the ALU instructions and the branch instruction. And then in the fourth cycle, which is the mem, you will see that I access the memory, okay, for read or write, and then the result of the ALU and the result of the memory, both they go and write to the register. So I have to be able to write two registers. So fundamental changes for the register file, and I have to accommodate all of this. Also, the sign extension I'll have to do for two instructions. One sign extension for the ALU and the other sign extension for the address calculation ALU. Okay, so this is what I need to update my hardware to allow static dual issue computation. Okay, now one thing we have to be careful with, or the compiler have to be careful with, hazards. So as more instructions are interacting, you will see that hazards will pop up and affect you within the packet. For instance, you cannot have these two instructions in one packet. Why? Because, well, you are adding a value of T0, and then you are using it to calculate an address. You cannot have those same because they cannot run concurrently on the same cycle because of the dependency, obviously. Load use hazards also impact these dual issue. So we still have to wait one cycle. So for example, if you are doing load and the result has to go to S1, and this is part of a packet here. Okay, so this is let me do this in a better way. Let's see. So suppose, for example, you have a packet here where you have a load on S1, so you're loading. So you cannot use S1 on the next packet, either here or here, because we know that it will take one cycle bubble. We have studied this in the hazard section. So you can use it rather in the following packet. Okay, so these are the kind of things the compiler has to worry about. Now, here's an example. Here's an example of a code that I am running this into um, um, sort of what I need to do. Basically, I have an array of data. Okay, I need to read this into register. I think it's T0, and add to it a constant which is S1 in S1, right? No, it's in S2. I'm sorry, it's in S2, and then return the value, store it back to where I read it. And I'm going to repeat this process for this entire array. The start of the array is saved in register S1, okay, and S1. So let's see, and I will go through the entire array, okay, as long as S1 doesn't become a zero. So that's probably, if my understanding is correct. Okay, I guess that was okay. So you can see here I'm loading the very first word into T0. Then what I need to do here, I'm adding to this T0 the constant S2, which is what I indicated here. Okay, and um, and then I'm saving back the word to the array. So that's what I'm showing here. And then what I'm doing, I'm decrementing this S by 4. Then I check if S1 reaches 0. If not, loop. If it reaches 0, exit the loop. Now, this is simple program. What happened if I take this program? Okay, first of all, I think I have a discussion here. Let's say this program, if I take this program and I run it on a simple pipeline, okay, and you can see, assume for example that S1, which is the length of the array, is 64. Okay, so you can see 64 what bytes. And the length of the array is 64 bytes, right? 64 bytes. But I know I need to read 4 by 4s because I'm doing updates by words. So how many words in this array? It is 64 by 4, and that is equal 16 words. So I need to loop through this loop by 64-bit if I need to implement this in a pipeline. So how many cycles I need if I'm ignoring the penalties for the jumps? Well, I need 16 loops, right? Every loop will take 5 cycles. Will take 5 cycles. Again, I'm ignoring the penalty of the branches, which means I need 80 cycles if I would to run this on a pipeline. Okay. Well, let's try to do this on a dual issue processor. Okay, so if we try to do this on a dual issue processor, what we need, we'll try to do put instructions in packet. This is a slot 0, this is a slot 1, okay? And in slot 0, you can see the very first slot 0 takes ALU and branch, and slot 1 takes load and store. Okay, the very first instruction load, okay, and followed going to T0 followed by T0, so I have to keep it alone here for the load instruction in slot 1. Unfortunately, I cannot have a adjacent alien instruction because all of these dependencies, so I have an no up here. Then what do I do? I did a swap here of these so I can update the SI, okay, I'm sorry, the S1, and then I can do this adding of S2 to T0. And why I didn't do it? I'm doing this because this will take another extra cycle, empty cycle. So I've used this instruction in this empty cycle. I moved it up, okay? And then at the end, I can do two slides. I can check for the branch. I can store the value back in the array. Okay. Notice here the four here he's used, and here's -4, and here when we stored it is 0, and the reason here it is 4 because we have already decremented s1 by -4, so you have so we can to return it to the 0, we have to add 4 here to compensate with the -4 up here. Okay, so in this array, how many instructions I have? 1, 2, 3, 4, 5. How many cycles? 4 cycles. So instructions per cycle is what? 5 over 4, which is 1.25. And ideally, the peak instruction per cycle is 2. The peak means the ideal. But because of dependency, we have used 1.25. So let's go back to our example. By using dual issue, we need 16 loops on this array. Every loop we need 4 cycles, which means that I need to execute this loop 64 cycles, which is an improvement from 80 cycles using just a pipeline. Not by a whole lot, but an improvement. Okay, so another idea is what we do is loop unrolling. And basically, loop unrolling, what it does, if I may use, see, if I may use the whiteboard here, what I'm going to do in the loop unrolling is basically, let's use the whiteboard here for a sec. Uh, the loop unrolling basically says the following. I have, suppose I have let's say, this is my array, okay? This is my array, okay? And I'm pointing with this array, this is my S1, right? And what I need to do is that I will copy those two registers, whoops, the register T0. And now there is nothing prevents me from copying those in parallel to different registers. And this is what we call register renaming. So I'm going to copy it to register 2 and register 3 because, and the compiler does that because it will now execute the 4 copies of the loop. So it will execute 4 loops in one iteration. So we will copy 4 words into these registers. We will add to them whatever we are adding, which is the S2 plus S2 plus S2 plus S2, and then we return them back to the memory. Okay, we will do this in one loop iteration. And this is what we call loop unrolling. You are kind of doing multiple copies of the small loop in one large iteration. Okay, so let's take go back to our example here and see how we are doing. So this is our two-way original loop without unrolling. This is unrolling, and we call it unrolled loop. Okay, using 4 copies of the original loop. So these are, well, I'll take 4 copies of this and write them in my original loop. Now, notice that this T0 is overused. I don't need to use the word, the register T0. I can use other registers like T0, T1, T2, T3. Using other registers or register renaming removes these fictitious dependencies, okay, and allow me to use multiple copies of the loop inside this major loop. And then, so what am I doing here? I'm loading the words right into the register T. Then what am I doing here? I'm removing. I'm sorry. I'm adding this constant, which is S in register S2. Then once I'm done, I'm storing back whatever values in these registers into back into these memory locations. Okay. Notice here, this is slot 1 and this is slot 0. Okay, and in slot 0, what am I doing? These are the add and the branch. And slot 1, what am I doing? These are the loads and stores. Okay, so I'm still keeping my dual issue organization for the packets. Also notice that because he moved up updating S1 up there, I have to be careful with the indices. Why? Because see here, the very first copy of the loop is we use 0 for the S1, index 0. Then after executing this statement, the S1 now is reduced by what? By minus 16. Notice in the second iteration, I should have used what? 4 here. But minus 4, I should have used minus 4. Let's see, I should have used let's see, it should be minus, in the second iteration, I should have used minus 4. Okay, so in the second iteration, I should have used minus 4. In other words, this index should have been minus 4. But because I have reduced S1 by a value of 16, I have already reduced it by a value of minus 16. So effectively what I do, I add 12 so that I get minus 4. So that's exactly what I have done. I add 12 to this to S1, which already reduced by 16. Effectively, I'm getting minus 4. Okay, so is this one, and so is this one. Now once I get these indices correct, I'll add this constant and then save them back. At the end, what do? I do the checking of the branch on the value of S1 if it reaches 0, and also storing the last word. Okay. Notice here, this is here for the very first one is 16 and here 0, and the reason here the S1 was not already subtracted, but here the S1 is subtracted, so I have to add 16 to the decrease S1 of 16 so that I get the index of 0. Okay, so in this loop, in this major loop, I have executed 4 minor loops of this loop. How many instructions I have? I have I have 14 instructions. So I have 14 instructions. Instruction per cycle equal 14 divided by how many cycle? 18. And what's my CPI? It is 8 by 14, which is 0.57. And we know that the smaller the CPI, the better it is. Okay, let's look at this here. Let's go to our so we are using dual issue with loop unrolling, where we unroll 4 copies of the original loop. Now notice, because I'm using 4 copies of the loop, my number of iteration will reduce by 4. Okay, so here 16, and now it becomes what? 4 loops. Now every loop of those takes 8 cycles, and this 8 coming from here. Okay, so that allows me to execute the entire program in 32 cycles, given S1 equals 64. Uh, okay, S1, this is a typo here. This it should say 64. This is a typo here. It should say 64. Okay, so S1 should say 64. Okay, so which means here 80 cycles in regular pipeline, dual issue without loop unrolling, 64 cycles with loop unrolling, 32 cycles and less cycles, it is better because CPU time will be reduced. Now, how about dynamic? Now we are switching. We were talking static issue. Let's talk about dynamic multiple issue. And this is what people like to call them superscalar processors, okay, as opposed to the VLIW processor or static multiple issue processors. And the CPU here decides, okay, and basically it decides whether to issue 0, 1, or 2, or 3 instructions, and all is governed to avoid structural and data hazard. Okay, and the compiler can help, but the main work is done by the CPU. Um, uh, so the CPU can execute things out of order, but we have to be careful and to preserve the dependencies between instructions. Okay, so for example, we can start executing the sub before this because there are no dependencies between these two. Okay, and here is a block diagram in one of these dynamic CPU. Here is the unit where we fetch and decode instructions. Now you have to know that the fetching, once we fetch and decode instruction, we have to issue them to what we call reservation station. The issuing happens in order, the way the CPU have seen those instructions coming from the program, and with the assistance of the compiler try to order them in an optimum way. Now every unit here, you can think of these mini CPUs or mini ALUs. Every unit here, we have integers, has a reservation station, and these reservation station basically are places for instructions to wait. So the processor has an add instruction, says, okay, which reservation station. You can think of these like tellers in a bank. So the CPU sees this teller is has no customer, so the CPU sends the instruction. Of course, integer instruction has to go to integer functional unit. Notice every functional unit has a reservation state because this is where the instruction waits. Okay, now you have integer multiple units. Every unit has a reservation station for the instruction to wait. Okay, for and this is the waiting because we need to resolve operands. We must have our values for the operands. Then these execution units finish execution of their instruction. Once an instruction has all the operands ready, we send it to the execution unit. It executes the instruction and it sends it out for the commit unit. When we send it out to the commit unit, what we do, we send the result of the execution unit out to the reservation station so that any instruction waiting for a data. So for example, suppose for example I have add something to T0. Okay, and I send this instruction to, let's say, and I send this instruction. Oops, let's see if I use this, and I send this instruction to here. Okay, to this in unit. Now suppose the following instruction, which is I'm doing sub on let's say S0 S0, and this S0 needs an operand which is a T0, right? Right. Notice I need it here. Suppose I send this to this reservation station. Okay. Now, once this instruction, the earlier instruction, execute, we will announce the result to all the reservation stations. So this comes here and tell it, you know what, the T0 is ready. The T0 is ready. Okay. So here is the T0. T0 is ready. Take it. So this instruction can start now. So these reservation station hold instruction until they get their operands. Once they are ready, they push them to the instruction to the functional unit, and then and then we send back the results quickly. Now, the commit unit, basically, this is where we write the values to registers and results to memory. This happens in order, in the same order the instructions arrive to the CPU. Now, there are reorder buffers or for register writes, and these are important so that when the instructions come out of order, we put them and commit them in the order. So in order, and so that's why we need the reorder buffers. So now register renaming and speculation. Of course, we need to rename registers in this kind of environment. You don't want to be stuck with a certain name of a register. You can rename any register to improve the efficiency of the dynamic execution, and also you do lots of speculative execution on jump and load instructions. So, for example, load instructions, you have to predict to try to predict the effective address, the loaded value, and all that because you don't want to stall your pipeline. Okay, with this, I conclude explaining the instruction level parallelism, and thank you very much.